This video gives a short overview of the course M7033T Scientific Computing with Applications in Tribology. The course is given during the autumn semester 2020 by myself, Andreas Almqvist, and my PhD student Kalle Kaliorin. We work at the Division of Machine Elements here at Luleå University of Technology. This course comprises the following 4 topics: contact mechanics, lubrication theory, which is abbreviated TFA for thin film approximation, wear modeling and simulation, and modeling multiphysics problems, abbreviated MPH, because we will use COMSOL multiphysics, and that's their 3-letter acronym of file name. Within the contact mechanics topic, you will learn about the complementarity problem, how to model elastic deflection or deformation, how to discretize integral equations for the elastic deformation problem specifically, how to work with linear complementarity problems formulations, and fast Fourier techniques for calculations of both derivatives and integrals, convolutions. You will also have a short crash course in artificial neural networks where you will study the correlation between surface topography data and contact mechanical outputs. The lubrication theory topic will start with the derivation of the Reynolds equation from the Navier-Stokes system of equations. In other words, it gives a presentation of the thin film approximation. Then finite difference method, FDM, for Poisson type of partial differential equations in both Cartesian and polar coordinates will be studied, and simulations of flows in bearings using the Reynolds equation you will do, and then predicting load carrying capacity, LCC, and minimum film thickness by means of fixed point iteration techniques. The wear modeling and simulation topic will start from the boundary lubrication perspective, and we will look at the Archer-Ware equation and how that can be used in connection to the contact mechanics model that we previously developed to perform numerical solutions for both abrasive and adhesive wear. The multiphysics modeling topic is the last one, and here you will be introduced to COMSOL multiphysics, and you will learn how to implement and solve the Reynolds equation in COMSOL. We will also learn how to model the solid mechanics in a thrust bearing, and then coupling the fluid and solid mechanics physics to simulate the fluid structure interaction in a thrust bearing. The underlying theory can be found in the course compendium, which is directly linked here to LTU's publication database DIVA. And as you can see, the content of this involves the dry contact problem, the lubricated contact problem, and how to model wear in lubrication also. However, there is no explicit chapter for the modeling of multiphysics problems. Based on what you have learned up to that point will be sufficient for you to grasp this and to be able to implement the multiphysics model suggested in COMSOL multiphysics. The teaching and course flow will be very similar for each one of the 4 topics, and it will be based on video lectures, question and answer sessions, and assignment. That's the core of each of the topic. You will be given an assignment or 2, and these will be carried out in groups which we will define for you, and then each of the topic will end with a peer review and discussion class where each group evaluates another group's implementation of the problem and presents the highlights and shortcomings they find, and thereafter we will discuss this openly in a whole class. The schedule looks like this, and I've highlighted some information here. So you can see you have a first introduction session here on 2nd of November, and it will hopefully be possible to give this physically in a classroom, but let's see what the COVID regulation says at that point in time. May be prepared to have this in Zoom instead. Then there are some orange blocks, and this is time allocated for you in the computer lab so that you can go there, and if there are people occupying computers, you can actually ask them to step away because you have the right to be there as you have allocated time. Then you have some purplish colored slots, and here these are the question and answer sessions. And then at the end of every week, starting from the second course week, we will have the peer review and discussion sessions. And it is very important that you in the mornings before these peer review and discussion sessions upload your code in the format which will be described to you. The last peer review and discussion session will be a slightly different one than the first four, and this will be an oral presentation by each of the group's findings, and then an open discussion will follow. The oral exam for this course will be on the January 7th of next year. The assignments, they are carried out in groups, and they involve both the theory and modeling aspect, and then the discretization and hopefully some pseudo coding to start with, then implementation and the numerical solution in MATLAB for the first four of them, and then in Console Multiphysics for the last one. The assignment is, as I said, partly examined via peer review and discussion, and then it is also examined via written report / oral presentation for the last one. The MATLAB implementations, they should be well structured and richly commented. And an example of such a structuring is given here. So you can see you have a division of 4 different sections within your code, and those are the input section, pre-processing section, the solver part, and then the post-processing section. And then specifically I've given an example how you can comment and really very well define a parameter which you use as input. Here we have u equals 10, and this is actually a sliding speed, and it has a unit of meters per second. And note that the implementation, the MATLAB code, should be handed in together with the report. During the peer review and discussion sessions, each group evaluates another group's MATLAB implementation. And then the MATLAB code is executed it is scrutinized and evaluated on structure on a scale of 1 to 5, readability and flow, for example, and then 1 to 5 scale on commenting, so presentation of solution procedure overview and concise descriptions of parameters and etc. Visualization, so the overall graphical presentation, labels, legends, axis limits, ticks, output in the command window, for example, and also the code efficiency. So if it's vectorized instead of using for loops, and if it avoids unnecessarily declaration of auxiliary variables, and it is very important that you highlight something positive and that you find at least some suggestion of an improvement. And the evaluation is done and handed in during class. So at least one group member must attend at each class. But all of you are responsible for the outcome. The MATLAB implementations of all the groups are then afterwards also openly discussed. The written report should be self-contained, written in a style of a technical report. It should give a comprehensive summary of the numerical implementations, and the level of detail should be such that another student with a similar background but who have not taken the course, they should be able to reproduce what you have done. And also note that you may use the report for the oral exam. And there is a very nice overleaf LaTeX report template available at the LTU web. You have it linked here. Lastly, we would like to thank you for applying for this course. And here are some small facts about it. It's actually a spin-off for a PhD course which was given first in 2010 and then 2013 was also given. But this second cycle or master level course was first given during the autumn semester 2014. And to start with, it was a blended, conventional and flipped classroom teaching style. And it has been repeatedly given each autumn semester until now, so 6 times before. This will be the 7th occasion. And the course compendium that we have mentioned here, it was actually established for the course given in autumn semester 2018, and it has been revised since then. You will have a brand new revision for this course. The PhD course was also given 2019 and will be given in the end of this year. And this year the course has been Corona adapted, which means it's fully flipped for this autumn semester 2020. We hope you will learn a lot during this course, and we also hope that we can meet you physically.